I have quiz number 2 right here. Everyone will get a quiz number 2. It is more reactions, okay, more and more reactions. And you must, I guess you'll hand that in a week from today, okay? So it's just more practice on doing reactions for the exam. Our first question was very simple, alkene nomenclature. In our first compound here, we're dealing with a 5-membered ring. We have 2 double bonds. We remember the rule. The rule says we're shooting for the lowest number at the first point of difference. And we want to give the alkenes the lowest possible numbers. We must number it in such a way that we go through a double bond. So 1 and 2 alkene carbons. With this one, we would want carbon 1 to be up here. We're going to go around the ring this way, so it's going to be a 1,3 diene. Have a methyl group in carbon 1. It's going to be a cyclopentadiene. Methyl group in position 1, double bonds in 1 and 3, and again a cyclopentadiene is our parent. Putting it all together, we have 1-methyl 1,3 cyclopentadiene. Any questions? Our next guy here is also going to be a diene. We're going to want to give our double bonds the lowest possible numbers once again. So this is going to be carbon 1 up here. We're going to go down this way. We're going to have a methyl group here. We're going to have an ethyl here. And please don't forget that we have stereochemistry around our double bond here. So this is a, quote, trans double bond, and we will write that as either E or Z. Oops. Methyl group in position number 2, so that's this guy. An ethyl in position 3. This is trans stereochemistry. Trans is actually E. And this is going to be a pentadiene. Putting it all together, E is our stereochemistry, 3-ethyl, 2-methyl, 1,3 pentadiene. Any questions? All right, our next guy, again, is going to be a cyclopentadiene. But remember, we have to give our double bonds the lowest possible numbers, and we must number through one of our double bonds. So carbons 1 and 2 must be alkene carbons. If we start numbering here, we're going to have a 1,3 cyclopentadiene, aren't we? If we started here, we would have a 1,5 or 4 cyclopentadiene. So the other one is a better way. That means our methyl group here is going to be at carbon 5. Lowest numbers to the double bonds, we number through the first double bond. Remember that rule. That means, once again, that this is going to be a 5-methyl. A 1,3 cyclopentadiene with a 5-methyl. 5-methyl, 1,3 cyclopentadiene. Any questions? All right, here we have a cyclopentane, and we have methyl groups on our ring. There is stereochemistry shown. There's actually two ways to name this thing. We can go to each of the carbons, our chiral centers here, and we can use R and S for those. We're not going to do R and S. The instructions said to use cis or trans in your name. So we can do that. As we number this thing, remember carbons 1 and 2 must be alkene carbons, and we're shooting for the lowest number sequence. That means we're going to let these be carbons 1 and 2, so our methyl groups will be in 3 and 4. The parent here is simply a cyclopentene. Our stereochemistry here is trans. We could use E. And we have methyl groups in 3 and 4. Again, the instruction said to use trans and not R and S. We could all do that, of course. We'll just call this trans 3,4-dimethyl cyclopentene. Any questions? All right, continuing, we also had 2 more molecules that we drew the structure. We're looking for 1,1-dichloro, 1-heptene. Now that's actually fairly simple. It's a hept, so we have 7 carbons. At carbon 1, we're going to have a double bond. So the way I would do it is to simply draw something like this. It's our 7 carbons, and I put my double bond here in carbon 1. This is also a 1,1-dichloro, which means that on this carbon, carbon number 1, we're also going to have 2 chlorines. So it should look something like this. 1,1-dichloro, 1-heptene. For methyl 2-hexyne. So we're dealing with a triple bond here. It's a hex, so we're dealing with a 6-carbon chain and a triple bond. The triple bond is in carbon number 2. So here's our 6-carbon chain. Carbon 2 would be this guy. So we simply have a triple bond. Now there's no way in the world that you would draw that because that's stupid. We know that our geometry here is linear, so please draw it properly, something like that. In carbon 2, we have our triple bond. Now all you have to do is count down to 4, 1, 2, 3, 4, and put in our methyl group. Any questions? For methyl 2-hexyne. All right, the next section on the sample exam was reactions. You can expect your real exam to be structured the same way as always. We'll have nomenclature first, and then we'll have a bunch of reactions and synthesis. Our first reaction. Remember, when you see reactions, you want to say to yourself what you know about them. and then simply apply it to the molecule itself. First, just talk about the functional group reaction, and then apply it to our molecule. We say we have HBr peroxide. What do we know about that? We know that this is going to be a radical reaction, that we're going to form the radical that's going to be most stable. Now that's going to be on the carbon. It would also form the most stable carbocation. We have a tertiary center and we have a secondary. So a radical is going to form at the tertiary center. Now that means that bromine radical must have added to the secondary center. So this is anti-Markovnikov regiochemistry. Once we form the tertiary radical, we pick up a hydrogen and we simply form the alkyl halide. Our next reaction, we have an alkyne. We have aqueous acid in the presence of mercury. Now we know that this is going to form an alcohol. The alcohol we form is very special. It's going to be an enol. The enol, we remember, is going to rearrange, tautomerize, to form a carbonyl. This is nothing more than acid-catalyzed hydration. So it's going to be Markovnikov regiochemistry. So we look at our molecule. We have a primary carbon and a secondary. The most stable carbocation would be on the secondary. That means that the oxygen, the OH group, is going to be on the secondary carbon. Now the enol is a transient intermediate. But we have decided that the oxygen itself is going to be bonded here. Once we form the enol, that will tautomerize to make a carbonyl at this carbon. So we have a methyl group here and a carbonyl. The product simply looks like this. Again, the logic you want to get through your head is that this is simple hydration. The oxygen is going to bond to the Markovnikov carbon and then rearrange to the carbonyl. In our next reaction, we have an alkyne anion. So we prepared this ahead of time. We took a terminal alkyne here in the presence of something like lithium amide. This is acidic, so it forms the salt, the alkyne anion, and the lithium cation. Can also do this with sodium. Our reactant here is bromomethane. So this is going to be a very simple SN2 reaction. The anion is going to attack the methyl group. Bromine is going to leave. SN2 reaction. All we're going to do is stick a methyl group on the anionic carbon. In our next reaction, we're adding HOBr to an alkene. Now it's a cyclic alkene. What do we know about HOBr? We know that we're going to form an intermediate bromonium ion. We know that that bromonium ion is going to be attacked by hydroxide anion. We're going to wind up with a trans allohydrin. That means hydroxyl group on one carbon, bromine on the other. The regiochemistry is such that the hydroxyl group will be bonded to the carbon that gives the most stable carbocation. Well, both of these are tertiary carbons, so it doesn't matter. All we have to do here is clearly show that the hydroxyl group and the bromine are trans to each other. Okay? So we're simply going to draw this, hydroxyl on one, bromine on the other, trans stereochemistry. Now I've drawn this as a perfect chair. I hope if you draw it, you also draw a perfect chair. I put the hydroxyl group and the bromine both equatorial, forces the two methyls axial. In reality, this would be a distorted ring, of course. These are slightly larger than the methyl groups, and that's why I put them equatorial. Any way you would have drawn it would have been fine, as long as you clearly showed trans stereochemistry. Any questions on these? All right. Here we have a substituted styrene, and we're doing hydrogen and platinum. Now we remember that this is a very powerful reductant. If you gave this whirling up in time and high pressure and all of that stuff, you could actually even reduce the benzene ring. But we're not doing that, okay? Not until chapter 14. So all we're going to do here is reduce our double bond. Now, for this reduction, what we have to remember is that we are going to simply convert double bond into a single bond and add 1 mole of hydrogen. The hydrogen will come on cis to each other. We have free rotation about this once we reduce it, so we don't need to worry about showing the cis stereochemistry. So all we're going to do is reduce this and make our single bond here. Once again, if it matters, remember the 2 hydrogens come on cis to each other. Our next reaction here, we have hydrogen and we have a Lindlar catalyst. Now, Lindlar catalyst is a porous nickel. This is equivalent to a, quote, poisoned catalyst. That means that it's really, really lousy. It's so bad that it will not reduce double bonds, but it's still powerful enough to reduce triple bonds. Still, just like hydrogen and platinum, both hydrogens are going to come on from the same side. So we're going to get partial reduction, but here it makes a difference. We have to show that the hydrogens come onto the same side of our alkyne, and that gives us the cis stereochemistry. Any questions? Our next reaction, we're doing hydroboration oxidation. Now we know that hydroboration oxidation is going to give us an alcohol. We look at our reactant here, and this is an alkyne. So the alcohol we're going to form is going to be an enol. Now, we remember that hydroboration oxidation gives anti-Markovnikov alcohols. We remember that. So we look at our starting material. Both of these are secondary carbons, but this guy is benzylic. Remember, benzylic carbocations are very, very stable. So that would be the Markovnikov carbon. So the oxygen in our alcohol is going to be bonded out here to to the other alkyne carbon. Now, because it's a triple bond, we're going to be forming an enol, aren't we? The enol is going to tautomerize to a carbonyl. So this carbon out here is going to be a carbonyl, and this guy will be a CH2. The product should simply look like this. Anti-Markovnikov enol tautomerize to the carbonyl. Any questions? Any questions on any of these three before we move on? All right, the next reaction we're doing permanganate. We know that there are two basic reactions we can do with permanganate. One is acidic permanganate, and that's going to split double and triple bonds. And the other is alkaline permanganate. Alkaline permanganate is going to make a 1,2 diol. We look and we see this is a simple alkaline permanganate. We're starting with an alkene, and so we're going to make a 1,2 diol. Now we remember that both oxygens from our diol are going to come from the manganate here. It's going to form a manganate ester as an intermediate that breaks down. But because both oxygens come from the MnO4, they're both on the same side of our double bond. That means we're going to wind up with cis stereochemistry. So we have a 6-membered ring. All we have to do is clearly show cis stereochemistry. Now I've done it here, again with a perfect chair. I have placed the hydroxyl groups here, axial equatorial, that's cis, relative to our methyl. This has 2 axial substituents. That's probably not the most stable conformation, so I'd probably flip that if it was needed. Again, you could show this with wedge bonds or whatever, as long as you clearly show that these guys are cis. Any questions? Once again, acid catalyzed hydration in the presence of mercury 2. We have a triple bond. We're going to form an enol. We look at our reactant here. We have a methyl group on both ends of our triple bond, so it's symmetrical. We don't have to worry about regiochemistry. We simply know we're going to form an enol on either of these carbons. That's going to convert to a carbonyl, and the other guy to a CH2. Very simple reaction, and we get the ketone. Our next reaction here, we have sodium liquid ammonia. Now, when it's written like this, we are talking about sodium actively dissolving in liquid ammonia. So it's fizzy. That is a radical process. We're going to generate hydrogen radicals. The triple bond is therefore going to be reduced. But because it's a stepwise reduction, we're going to get the most stable conformation. That is, we're going to generate the trans double bond. triple bond is simply going to go to a double bond. And again, we must show trans stereochemistry. Our next reaction, we're doing ozone, followed by dissolving metal reduction. We know that ozone reacts with double bonds to form an intermediate ozonide. The ozonide is stable enough that you have to use dissolving metal reduction to get rid of it. When you do that, effectively you split your carbon-carbon double bond. Each of the alkene carbons becomes a carbonyl. Ozonolysis is a very gentle oxidation. That means that we can produce aldehydes and ketones. We don't oxidize the aldehyde once we make it. So you simply have to mentally split your double bond. Each of these carbons becomes a carbonyl. We are going to have this simple aldehyde, this carbon, and our terminal carbon here will give us formaldehyde. Very useful reaction because aldehydes in general are useful intermediates, but they're difficult to make. The problem with trying to make them is these oxidize easily to the carboxylic acid. But ozonolysis works very nicely. Any question on these four before we move on? All right, our next reaction. This is a per acid, isn't it? Our first oxygen here is actually a carbonyl, and then we have OOH, a per acid. All right, what do we know about per acids? Per acids react with alkenes to form epoxides. However, this also has a second step, where we take the epoxide product and we dump it into aqueous acid. Now remember, the epoxide is strained, so it will easily undergo ring opening. When it does that, it will form a 1,2-diol. Because of the geometry of the epoxide, the hydroxyl group will come in from the opposite face, and you will make a trans 1,2-diol. We have a ring, so we can show that. All we have to do is show our stereochemistry. This is our immediately formed epoxide. All I've done is put the oxygen right here where our double bond was. And then step 2, we do our ring opening. And we form a trans 1,2-diol. Any questions? So just recalling what we know, if we do alkaline permanganate, we get a cis 1,2-diol. If we do per acid followed by aqueous acid, we get a trans 1,2-diol. All right, another permanganate reaction here. This is acidic permanganate. We know that acidic permanganate is going to split double and triple bonds. We are dealing with an alkyne here. So we're going to split our triple bond. When we do this, each of the alkyne carbons will become a carboxylic acid. So each of our alkyne carbons is simply a carboxylic acid. So mentally, you simply split this. We're going to have a 2-carbon carboxylic acid. This carboxylic acid will have a benzene ring attached. So it's benzoic acid on this end and acetic acid on the other. Our next reaction here, we have chloroform with aqueous KOH. Now, that undergoes a 1-1 elimination. What KOH does is pull off hydrogen, chlorine leaves, and we form dichlorocarbene. Now remember, dichlorocarbene is neutral. Its carbon is trigonal. It has 2 chlorines, a lone pair of electrons on the carbon, and it's very, very, very electrophilic. We have a double bond here. Dichlorocarbene is simply going to react with our pi system here, sit down on top of it, and we're going to form a dichlorocyclopentane. Carbon simply adds to our double bond here, and of course we have the 2 chlorines left over. Something like that would work. And we have converted our double bond to a cyclopropane ring, and we have 2 chlorines left from our dichlorocarbene. This is the part that added right here. And our last reaction in the set, we simply have an alkene, and we're doing hydration with aqueous acid. Now what we know about this is that this is going to form a carbocation intermediate. We're going to form an alcohol. The carbocation is going to be at the center that is most stable, so in this case it will be the tertiary carbon. And we're simply going to add OH to our tertiary carbocation. Product should look something like that. Simple Markovnikov regiochemistry. Any questions? Now, I haven't quite finished your exam. You may have essentially the same number of reactions. You may have a little bit more depending upon my mood. Any questions?
How are you feeling right now?
I am really tired. All right. This is kind of baby synthesis. All I'm asking you to do here is to start with something on this side and make these molecules. And what I want you to do is simply put in the reaction conditions. Now, like I said before, the way these exams are structured, you're going to have 20 or so reactions on the first couple pages. These have all the reaction conditions, don't they? So you don't have to worry about remembering everything exactly, as long as you can just flip back and forth and remember basically the functional group reactions. So what we're doing here is we are converting an alkyne to an alkene. So that's a reduction, a partial reduction. And we are getting trans stereochemistry. You should recall that we can get trans stereochemistry with dissolving metal reduction. So this is either going to be sodium or lithium in liquid ammonia. Again, stepwise reduction to give us the trans stereochemistry. Here I did sodium actively dissolving in liquid ammonia. Remember, this is different than sodium amide. Sodium amide is a very strong base. That's sodium previously dissolved in liquid ammonia. Our next reaction, we're taking an alkyne and we're making an alkene again, so it's a partial reduction. And we are winding up here with cis stereochemistry. That means that we're adding both hydrogens to the same side of our triple bond. And it's because it's a partial reduction, we have to use a poisoned catalyst. We could use something like platinum or palladium on barium sulfate, that's poison, or we could use Lindlar catalyst. Cis stereochemistry, therefore a poisoned catalyst. Again, there are two that we know. Hydrogen gas, Lindlar catalyst, or we could do hydrogen, platinum or palladium on barium sulfate. And our next one here, we are taking an alkyne and we are simply making a ketone. This is symmetrical. Don't have to worry about regiochemistry or whatever. We simply have to hydrate our triple bond to form an enol. There are two ways we know to do that. We could do aqueous acid in the presence of mercury 2, or we could do hydroboration oxidation. Because this is symmetrical, it doesn't matter. The simplest would be to do hydration, and again, that's aqueous acid in the presence of mercury 2. Mercury 2 or hydroboration oxidation. Any questions on these? In our first one here, we look and we see we have an alkyne and we're splitting our triple bond. Really, the only way we know to split a carbon-carbon triple bond is by permanganate oxidation. And again, that's going to be an acidic solution. So we want acidic permanganate. We have a 4-carbon alkyne. We're making two carbon carboxylic acids. Only way we know to do this, like I said, is acidic permanganate. And our last one here, we have an alkyne with 1, 2, 3, 4, 5 carbons, and we're making an alkane with 1, 2, 3, 4, 5 carbons. So this is simply total reduction. We want a powerful reducing agent, something that will reduce the intermediate alkane. The only way we know to do that is one of our heavy metals, either platinum or palladium on carbon, in the presence of hydrogen gas. Complete, full reduction. Any questions?
So how are we supposed to know that we needed two of those compounds there? Did you not put the two on the sheet? No. Not hydrogen. I'm not talking about hydrogen. Two of those over
Oh,
there.
these guys?
Yeah. We only have one on.
Oh, you do? Okay. Well, you
So
should have two.
there's supposed to be two there?
Yeah.
Okay.
The two's fine.
That's
Because
I
we're
just
going to
wanted
split
to
it
make
into
sure.
two things.
Yeah, there's two.
All right. In this one, we are going to do a mechanism. You will have mechanism questions on the exam. They'll look pretty much like this, little boxes that you put stuff in. We see we are doing HBr peroxides. We know that this is a radical reaction. We have an alkene, and the first step in this is going to be addition of bromine radical to form the most stable carbon radical. Now we look at our alkene here. We have a tertiary carbon. This is actually a secondary, isn't it? Except this is also benzylic. Because it's benzylic, it is more stable than the tertiary. So the radical is going to form on the benzylic carbon. So what we're supposed to do is to draw your initially formed radical intermediate. And this is going to be, again, on the benzylic carbon. Step one, we add bromine radical to get the most stable radical we could form. Once we've made the carbon radical, that's very reactive. It will react with another mole of HBr. It will pull a hydrogen off, hydrogen radical. Hydrogen radical, hydrogen will go here. So this is now going to be a CH2. And we have formed the anti-Markovnikov alkyl halide. No stable radical. Pick up a hydrogen atom, anti-Markovnikov regiochemistry. Any questions? All right, here we're doing a more traditional synthesis problem where I simply give you the final product. I want you to do this beginning with an appropriate alkene. We can do this in one step. All right, what you do is you look at your final product here, and you're going to ask yourself your basic questions. That is, what is it? What is the regiochemistry? And how do I know to make it? We look at this, this is simply an alcohol, isn't it? We know two ways to make alcohols, beginning with an alkene. One is simple acid-catalyzed hydration, or reaction with mercury 2. That gives us Markovnikov alcohols. The other is hydroboration and oxidation, and that's going to give us anti-Markovnikov alcohols. We look at this, we see the OH is bonded here to a terminal carbon. So this used to be our alkene. This is a benzylic center, and that would be the most stable carbocation. So we look at this and say, this is anti-Markovnikov. OH is bonded adjacent to the most stable carbocation. Only one way that you know to make it. Again, This used to be the carbon-carbon double bond. The reaction conditions, this is our starting alkene. The reaction conditions, simply hydroboration, oxidation. Any questions? All right, our next one, again, is a mechanistic question. We're supposed to draw the initially formed bromonium ion, and then, of course, our final product. Now, what we're doing here is simply adding bromine to a carbon-carbon double bond. We know that this reaction proceeds by the formation of an intermediate bromonium ion. That is, one bromine simply bridging our two alkene carbons. And then in the second step, Br- attacks that from the opposite side to give us a trans 1,2 dibromide. So that's what we know. The bromonium ion, we're simply going to take and add a bromine across these two carbons, and it will have a positive charge. Bromonium ion would look something like this. Again, the bromine bridging the two alkene carbons, and the whole thing has a positive charge. Now our second step, Br- is going to attack. It's going to ring open the bromonium ion and form the trans 1,2 dibromide. Br- is going to come in from the backside here, a ring opening. Opposite face, probably attack here, get away from the methyl. And we form a trans 1,2 dibromide. If you have a problem like this, please take the time to show the bromonium ion clearly and make sure that you show the stereochemistry of your final product. Any questions? All right, our last question on the sample exam here. We simply have an alkene, and we're adding HBr. There's no peroxides present. We know that this is going to be an ionic addition. That's step one, we're going to protonate our pi system. That's going to rearrange to give the most stable carbocation. So we look at our starting material here. We have a tertiary center and a secondary. The most stable carbocation is going to be at our tertiary. As we need to show in our first box, the structure of the most stable carbocation. So the charge is going to be here, and it should look like this. Our final product. All in the world we're going to do is take Br-, going to add it to the most stable carbocation. So this is Markovnikov regiochemistry. When we do that, we simply generate the tertiary alkyl halide. Remember that because this is a carbocation intermediate, if we formed a carbocation somewhere out here, that it would rearrange until we finally got to the most stable carbocation that the molecule could form. Any questions? Now, once again, this is a guide as to what the actual exam will look like. And this is quiz number 2. Again, it's just a bunch of reactions here. This is due on the day of the exam.
If we do this, we're probably going to be really good.
Anywhere that I put X, okay, like HX or X2 or something, I'll just pretend that says bromine. Okay? So any questions?
Will there be any extra credit for this test?
Of course there'll be an extra credit. Of course it will. All right, once again on Thursday, we will do the SN1 reaction, and we will verify our product using infrared spectroscopy.